Welcome to part 4 of transformation of functions. Today we're going to look at horizontal shifting. If we graph y equals the quantity x minus 4 cubed and y equals the quantity x plus 2 cubed in your calculator, you will see some interesting comparisons. A, from which basic function are these functions built? B, what's the effect on the graph of adding a constant inside the function? Now, the important thing to note here is that when we say inside the function, we mean inside these parentheses. It's like a substitution into f of x. So instead of just having f of x equals x to the third, we now substitute a horizontal shift. If we want to go to the left, we add inside the function. This will shift to the left, and now we have x plus c to the third. This will shift us to the left, assuming c is greater than 0 or positive. Similarly, f of x minus c would give you x minus c quantity cubed, and that would shift to the right, assuming c is greater than 0. Adding a constant to the input of a function shifts the graph horizontally, which is what I just said, but we'll go ahead and read the page. To the left if the constant is positive, and to the right if it is negative, or subtraction. The value of f of x minus c at x is the same as the value of f of x at x minus c, supposing that c is greater than 0. To graph y equals f of x minus c, shift the graph of y equals f of x to the right, c units. This might be helpful if you draw a little arrow whenever you see the shifting inside the function. And to graph f of x plus c, shift the graph of y equals f of x to the left, c units. If we use the graph of f of x equals the square root of x to sketch the graph of g of x equals the square root of x plus 5, and h of x equals the square root of x minus 3. If we look at g of x, we can see we're going to shift to the left 5 units, and for h of x, we're going to shift to the right 3. Let's first graph our function square root of x. For an input of 0, we have 0 as an output. At 1, we have 1 as an output. At 4, we have 2 as an output. And at 9, we have 3 as an output. Now I need to shift it to the left 5 units. This will give me g of x. Remember, this is f of x. If I shift it to the left 5 units, 0 will now be at negative 5, 1 will be at negative 4, 4 will be at negative 1, and 9 will be at 4. So g of x has been shifted to the left 5 units. It is the opposite of what you might expect when you're working with these functions. Now let's graph a standard square root. 0 gives me 0, 1 gives me 1, 4 gives me 2, and 9 gives me 3. Now let's graph h of x, which is going to be the square root of x minus 3. Now remember, that shifts my function to the right 3 units. So 0 is now at 3, 1 is now at 4, 4 is now at 7, and 9 would be at 12. So it would be right about here. If I connect these dots, that is my new function, h of x. Without using a calculator, sketch the graph f of x equals the absolute value of x minus 6 plus 2. What this is asking is for you to combine both the vertical and the horizontal shifts. We know that a standard absolute value function is a V-shape. So at 0 you are at 0, at 1 you're at 1, at 2 you're at 2, and to the left at -1 you're at 1, at -2 you're at 2. So it has this kind of V shape. That's just a standard absolute value graph. Now, since we have subtract 6 on the inside, that means we need to go to the right 6 units. All my x coordinates will now be shifted 6 units to the right. Don't forget one more thing. So this would be my shifting horizontally. Now all my y values, or y coordinates, will be shifted up 2 units. So my new absolute value function will look something like this blue line here, where my lowest point will be at 6, 2. Now let's take a look at the graph on the left. It shows the function g of x, but there are some very obvious intersections that we can use for our transformation. We can use the graph of g of x to create the graph of g of x plus 3 inside, x plus 3 is inside, and then shifting up 5. The plus 5 is on the outside of the function. That means that I'm going to shift my function to the left 3 units and up 5 units. I'm going to start with the point -3, 1. First, I'm going to shift it to the left. That affects the x coordinate. So instead of being at -3, I'm now at -6. And then instead of being at 1, I'm shifting up 5. So now I'm at 6. So my dot that was at -3, 1 has now been transformed to this point here. I know that anything to the left of this point will just be a horizontal line because that's what it was before. Now let's take the point -1, -2. Let's transform it to the left 3. So subtract 3 from -1, that's going to be -4. And then let's add 5 to the y coordinate because that's our shift up. So that will be at 3. 1, 2, 3. And now I can connect those dots. And hopefully you are seeing a resemblance to what we started with. Let's pick the next coordinate point. So this is now this point here. Our next coordinate point is the point 1, 2. I'm going to shift it to the left 3 places, 3 units. So subtract 3 from 1, that will be -2, and then add 5 to 2, that will be 7. Connecting that dot gives me the next piece of my transformation. This is the coordinate point 2, 2. Shifting my x coordinate to the left 3 places gives me -1. Shifting 2 up 5 gives me 7, so this is my new coordinate point. And I just continue this process moving on. The next coordinate point that's obvious is 5, -3. So I shift the 5 to the left 3, so subtract 3 from 5, and that's 2. And then I need to add 5 to -3, so that will be up 2. And now I can connect these points. And notice this slope continues on, so I can extend this down. But the general shape of the transformation is now graphed. The big takeaway here is if you are shifting things to the left, you are subtracting from the x coordinate. And if you are shifting up or down, in this case we were adding, because we were shifting up, add to the y coordinate.